Hello all, welcome. This is the second time we are doing the PhD students talks. So I hope you have a wonderful time. Thank you to Danielle, Ali, Sevil, and Zhiliang for giving the talks. Sorry for butchering your names. So Danielle is a second year PhD student working with Dr. Gang Wang. She studied at Johns Hopkins and then UM, and now she's doing a PhD conducting research in energy efficiency in HVACs. Ali is a PhD student in civil engineering at UM. He works on sustainable construction materials and protective coatings for enhanced infrastructure durability. Sevil is a PhD student also in CAE. She works on genetically engineered peptides to mitigate metal corrosion. And finally, Zhiliang is a PhD student in Dr. Sharmin Shi's group. He's working on rebar protection using sacrificial anodes and on cement-based batteries. So thank you very much, guys, for doing this. We'll go in the order of Danielle, Ali, Sevil, and Zhiliang. You have approximately 11 minutes for your talk and a few minutes for question and answers. So thank you. Danielle, all yours.
Okay. Share my screen. Okay, you can see my screen?
Yep.
Okay. All right. Yes. Hi, everyone. I'm Danielle. I'm going to be talking about performance improvements of single duct air handling unit systems under different controls. So I'm going to go through some background, state the objective, go through methodology, show some results, and then we'll conclude. The system I'm going to be talking about is the HVAC system. So HVAC, it stands for heating, ventilation, and air conditioning. And it's responsible for two things. Number one, maintaining indoor air quality at carbon dioxide levels less than 1,000 ppm. And then the second responsibility is to maintain indoor thermal comfort. So making sure that the air inside of the building is at 75 degrees Fahrenheit and 50% relative humidity. So we know our desired conditions, that was the CO2 levels less than 1,000 ppm, 75 degrees Fahrenheit, 50% relative humidity. Now, what kind of disturbances are there taking us away from those desired conditions? So these would be our system loads. So first of all, looking at indoor air quality, so we have our CO2 load, that's people. People generate about 0.0106 of CO2, CFM of CO2 per person. So to mitigate those effects, our system, our HVAC system, has to provide about 15 CFM of outdoor air per person. And then looking at indoor thermal comfort, so we have cooling loads and heating loads. And so here I want to be clear, a cooling load are things that heat the space. So our system has to cool them. Same for heating load. These are things that are cooling our space. Our system has to heat them. So for cooling loads, we have people, so they emit heat and moisture about 130 watts per person. Then we have office equipment, lighting, heat transfer through the envelope. So office and equipment and lighting, about 1 watt per square foot for each of those. Those are all our cooling loads. So our system has to provide dry, cool air in order to get us back to that 75 degrees Fahrenheit, 50% relative humidity. And then for heating load, we can have heat transfer through the envelope, through the building envelope, creating that heating load. So our system would have to provide hot air. Now looking at the overall configuration, here's a schematic of an HVAC system. So to orient ourselves, we have our outdoor air intake. Then the air will go through the cooling coil at the air handling unit, through the ductwork, through the reheat coil at the terminal boxes. And then the air is in the zones. So the zones are the rooms of the building, for example. This is where the people are. And then the air goes through the return duct. Some air gets released as exhaust, and the rest of the air will cycle back through the system. And the fans are what is responsible for moving this air around. So as for our energy consumption, we have cooling energy at the cooling coil, heating energy at the reheat coils, and then electricity at the fan. And so the two pieces of equipment that we're really going to be focusing on, one is the air handling unit, and the second is the terminal box. More specifically, we're going to be manipulating the supply air temperature. So that's the temperature after the air handling unit. And we're going to be changing the minimum flow rate. That's the air flow rate at each of the terminal boxes. So those are the two things we're manipulating. And just to understand a little of terminal box operation, so we're changing, I'm going to bring up the little laser pointer, the minimum flow rate. So here for terminal box operation, you can see the top right corner here is your 100% design load and 100% design airflow. So given your certain load, you want to get to 75 degrees Fahrenheit, 50% relative humidity. This 100% is the airflow that's needed to do that. And so as your load decreases, your airflow can decrease until you get to this minimum airflow rate, which here is 30%. And that's to maintain adequate ventilation. So you need that at least 30%. And we're going to manipulate this number here. So all of this takes energy, right? The whole system. Here you can see to the left a pie chart of US commercial building energy consumption. This data is from 2018. And then to the right here, a more global look at building energy consumption. And you can see that HVAC accounts for 40 to 50% of a building's energy consumption. So a significant part. So the overall goal is to decrease the energy consumption of achieving adequate indoor air quality and thermal comfort. So those two things, keeping the CO2 levels less than 1,000 ppm, maintaining 75 degrees Fahrenheit, 50% relative humidity. We want to maintain those indoor conditions and try and decrease the energy consumption that takes. So then more specifically, looking at the objective of this study, we wanted to demonstrate energy savings of a system with optimized supply air temperature and minimum airflow controls while maintaining indoor air quality and thermal comfort. And I wanted to include this figure to the right here so you can kind of visualize. We have our HVAC equipment, the air conditioning equipment throughout the building, and it's all connected through controls. Maybe you've heard of a building automation system. So you can manipulate different parameters to achieve desired indoor conditions. And so what we're manipulating, like I said, is the supply air temperature at the air handling unit and the minimum flow rate at the terminal boxes. So there's no change to hardware. We're just changing controls. Our baseline case here is first for the supply air temperature, keeping the supply air temperature at 55 degrees Fahrenheit. That's to maintain the room at 75 degrees, 50% relative humidity. So baseline has 55 degrees Fahrenheit fixed and then a minimum flow rate of 30% fixed during occupied and unoccupied time. That 30%, like I said, is to maintain indoor ventilation requirement, making sure there's adequate ventilation in the space. Then for our improved case, during the winter time, we're going to increase that supply air temperature to 65 degrees Fahrenheit. So remember, this is the supply air temperature after the air handling unit. So the increase in supply air temperature will decrease the reheat energy consumption because now it's 65 degrees Fahrenheit. The air doesn't have to be heated up as much. Then for the minimum airflow rate, we have during occupied time, so this is working hours, 8 a.m. to 5 p.m. There's people in your space. You want to make sure that the airflow rate is still 30%. But during unoccupied time, there's no one in the building, so it's outside of working hours. We can reduce that flow rate to 10%. And so then this will reduce the fan energy consumption because remember that the fan is responsible for moving the air. And so we're decreasing that minimum airflow rate. So those are our two cases that we're running. And here for the methodology. So we ran those two cases through a software called Energy Plus. It's a Department of Energy software. You put in there the location of your building. So we chose Atlanta. It uses Atlanta weather data. Then we chose a default medium office building. This is from the Department of Energy. And you put in there the different parameters that you're changing. So we ran the baseline case, the improved case, and then Energy Plus will give us the energy consumptions and we can plot those in Excel. So here you can see the results. We have a heating load decrease by 72%. So this is from increasing supply air temperature from 55 degrees Fahrenheit to 65 degrees Fahrenheit in winter Remember I said the heating load. So heating load means things that are making the space colder. So you have to heat them up. Here we have a supply air temperature that increased. So the heating load decreased, great, by 72%. Then for the fan power, it decreased by 8.1% by decreasing that minimum airflow rate during unoccupied time when we didn't need all of the ventilation that came with 30%. So we saw 8.1% decrease in fan power consumption. Then for the overall HVAC electricity, the energy consumption decreased by 19.7%. So this includes everything, the heating power, fan power, cooling power. So just by manipulating the controls, we were able to decrease our energy consumption by about 20%. So just to reiterate, wrap everything up, in conclusion, by increasing the supply air temperature from 55 degrees Fahrenheit to 65 degrees Fahrenheit in the winter and decreasing minimum airflow rate from 30% to 10% during unoccupied time, so only making changes to controls, no changes to hardware, the single duct air handling unit system achieves 20% energy savings, and we maintain indoor air quality and thermal comfort. So 20% energy savings. To continue this study, we're planning to add more energy efficiency measures. And also we tested this for Atlanta, which has a warm, humid condition. So it'd also be good to go through this in different climate zones and see how the changes in controls would impact that. So that's all. Now I can go for questions.
Fantastic. You were perfectly on time as well. So we have a few minutes for questions.
I'm going to stop sharing. Okay. Thank you, Sophiana. I see your claps.
I think at the end you mentioned Atlanta, right?
Sorry?
At the end you mentioned Atlanta, right? That this was done in Atlanta. Did I hear you right?
Yes, yeah. The building location in the simulation is Atlanta. So they use Atlanta weather data.
Gotcha. Any particular reason why that was chosen?
It just had a pretty, you could kind of see all the effects during all the different seasons. Like at first we had data for Rochester, New York, I want to say, and it was really difficult to see the different changes in the transition seasons because a lot of times like in the fall or in the spring, it was just cold, whereas Atlanta had more differences in the temperature. So you could really see how the energy consumption changed.
So I think you've already answered this, but the question is, have you considered other locations?
So yeah, Rochester, I guess, but that's kind of the future. Yeah.
Yeah, no, both the questions came in at the same time. So anyway, okay. Any
Thank
other
you.
questions? I don't see anything. Fantastic work. Ali.
Okay, let me share my screen. Do you have, oh, wait a second. Okay, do you have my screen?
Yes, just full screen it, please.
Awesome. Just a second. There you go.
Great, thank you.
Okay. So hello, everyone. Today, I want to present a part of my research, micro nano engineering of epoxy coating for steel rebar in concrete anti-corrosion and bond performances. Have you ever noticed that annual cost of corrosion for highway bridges in the US in $13.6 billion? Just check these images of concrete piles deteriorating in the ocean in Florida. It is obvious that we need innovative solutions to address this issue. But what is actually rebar corrosion? Basically, rebar is already passivated inside the concrete, which means there is a protective oxide layer on the surface that protects rebar from corrosion. However, chloride ions, like the corrosive species like chloride ions from the outside environment, penetrate the concrete over time, reach the surface, and destroy the passive layer. And once the layer is compromised, rebar starts to corrode, making a lot of rust on the rebar, forming a lot of internal stresses, leading to cracking, spalling, and delamination. Organic coating provides a solution for this issue. However, they lack active corrosion protection and poor bonding. Here is an example of using organic coatings for rebar. Picture number 1 is uncoated rebar embedded in concrete after 244 days of corrosion test, exposure to a harsh environment. And as you see, there are a lot of corrosion products on the surface. However, for picture number 2, which is coated rebar, the extent of corrosion products substantially lower, yet we have some tiny spots of corrosion on the surface, which is related to maybe pre-existing damage on this sample. And basically, it doesn't matter for rebar corrosion because the type of corrosion in concrete is localized. So it doesn't matter if you have a large surface area like figure number 1 or you have a tiny spot. The damage is going to be the same. And this is because the coated conventional coatings doesn't provide active corrosion. They can only protect the steel passively, which means they can act only as a barrier between corrosive species and rebar. And once the coating is damaged, they will be no longer protective. And we can't just simply add active materials like zinc powder inside the coating because the concrete environment is highly alkaline, and the active material starts to react with calcium hydroxide and convert to a different material, a passive and useless material. Like I mentioned it before, adhesion bond between coated rebar and concrete is another issue. Picture number 4 shows bond strength between uncoated rebar, blue line, and coated rebar, red line, for 3 different types of concrete. As you see, for all types, coated rebar shows lower bond strength compared to uncoated rebar. And this is because when you apply an organic coating on the surface of rebar, you make the surface slippery. Also, you change the surface chemistry from hydrophilic to hydrophobic, and concrete is hydrophilic. Now coated rebar is hydrophobic. They don't like each other. They're not compatible. And these prevent both physical and chemical bonding between coated rebar and concrete. In my research, I used micro nano engineering to develop a 2-layer epoxy coating to address these issues. For the first layer, which is primer coating, we hypothesized that if we can have some smart nano reservoirs that can release active agents only when it's needed, we can solve this problem. Basically, these small nano reservoirs are selective. What they do is they keep monitoring for they don't react with calcium hydroxide, and they're only responsive to corrosive species. They keep monitoring for the presence of chloride ions, let's say, and then when they're exposed, they will be triggered and release active agents in the coating. And for top coating, we hypothesized that if we can apply some abrasive materials like bone ash, like crushed glass, we can change the surface chemistry from hydrophobic to hydrophilic. And then we can also introduce some texture. We can make the surface rough, and we can improve bonding between coated rebar and concrete. To evaluate our coating, we used weight loss measurements, salt spray, and pull-off test. What we did in weight loss test, we applied 3 different coatings on the surface of steel, including epoxy coating, pure epoxy coating, which was control sample, epoxy coating containing a commercial active agent, and epoxy coating containing the same active agent, but here loaded inside a smart nano reservoir. And then we applied the coating on the surface of steel, and we submerged the sample in simulated carbonated concrete pore solution for a specific time. And then we observed 9.3 milligram of weight loss for control sample with a lot of rust at the bottom of the beaker, and 6.2 milligram of weight loss for epoxy coating containing active agent, and only 2.4 milligram weight loss for epoxy coating containing a smart nano reservoir. And the extent of the rust, as you see, is substantially lower than two other samples. In salt spray test, we applied the coating on steel plates, and we intentionally produce a damage on the surface of the coatings. And we placed the samples in salt spray chamber, where the samples are continuously exposed to a fine mist of salt water. And we visually investigated the corrosion products on the surface of samples over time. And after 28 days of exposure, we realized we observed a lot of rust on the surface of control sample. And after adding 1 and 5% of smart nano reservoir, the amount of rust was decreased. And this is because the high performance of these coatings is because these nano reservoir, like I mentioned before, they release anti-corrosion inhibitors or active agents gradually over time and when it's needed. So that increases the performance, anti-corrosion performance of the coatings. For pull-off test, we use, basically in this test, a fixture or dolly is attached to the surface of the coating and a vertical tensile load is applied until the coating detaches. And the force at which the detachment occurs is recorded as bond strength. We use these samples, steel plates, uncoated, epoxy coated, garnet, bone ash, and crushed glass with different particle size. And then the samples were mounted in fresh concrete. And after 28 days of curing, the samples were ready for pull-off test. For uncoated steel, pull-off bond strength was found to be 3.3 megapascal, which was impressive, and the failure mode was found to be substrate failure, which means concrete block failed before the detachment. For epoxy coated, the value was found to be only 0.8 megapascal, equal to 76% decrease, and the failure mode was adhesive. And for the best samples, the abrasive coated samples, which was bone ash, the bond strength was 2.6 megapascal and equal to only 21% decrease compared to uncoated sample. And the failure mode was found to be cohesive with visible detachments of concrete on the surface of coating. And like I mentioned earlier, this is because when we add abrasive material on the surface, so we improve the bonding both physically and chemically because we change the surface chemistry and we introduce texture on the surface. In general, the research aims to address rebar corrosion and bond issues using surface engineering. Nano engineering of primer coated provided long-lasting and improved corrosion protection. Microengineering of top coating enhanced bond strength. And in general, two-layer epoxy coating can provide extended life service, higher durability, and enhanced sustainability. Yeah, and that's it. Thank you so much. If you have any question, please feel free to ask me.
Thank you very much. Questions or comments? So one question from my side, what is this bone ash and why are you using bone ash?
Because we wanted to have to add values to waste material. So we used crushed glass, like waste crushed glass, and then we have a lot of bones from like different animals after selling them. So we have the bones like just dumping inside the environment. So we take them, we calcinate them, and we crush them, and we convert them to bone ash. And then we can use them as for different types of applications.
Could you estimate the amount of bone ash that is available, roughly?
I don't have any idea. I have the numbers, but I don't remember the numbers.
Thank you. Any other questions or comments? Okay, I don't hear anything. Thank you very much again.
You're welcome.
Sevil? Full screen, please. No, it's yeah, perfect. Thank you. We can't hear you unless this is me. Can someone hear Sevil?
No.
Can you hear me now?
Yes. Yeah, please start.
Yeah, sorry. So should I start from the beginning?
Yes, please.
Hello, I am Sevil. I'm a second year PhD student, and I will present today methionine functionalized pool aspartic acid, which is a sustainable solution for enhancing the corrosion resistance of the metals. So this is my outline. I will start with the introduction part and go with some research objectives. I will give some details about the materials and the methods, some results in the inhibition mechanism of the pool aspartic acid this inhibitor, and go with the conclusion. Corrosion is a natural phenomenon caused by the electrochemical reaction that results in the degradation of the metal with time. So it significantly shortens the lifespan of the steel structure, and it's very important for many of the industries. And it's leads to the economic loss due to these repairs and the replacement things. And for the economic aspect of the corrosion for the industry, globally, corrosion-related costs account $3.5 trillion, so which is the 3.4% of the worldwide gross domestic product. So it's a very huge number. And when we look at from economic cost to safety concern, this is the pie chart showing the distribution of the incidents in gas transmission line for 4 years. And it shows the corrosion incidence due to corrosion. It has the 20% ratio for this, and which is very high for these type of incidents. And to prevent those corrosion, generally corrosion inhibitors used, which is the method based on the addition of some chemicals, which is effective and the very cost-efficient method. But the use of inhibitors in industry contain toxic materials and which are not environmental friendly. So there's some need for sustainable and non-toxic alternatives. To this end, we are trying to develop an environmental friendly and a polymer-based corrosion inhibitor and understand its mechanism to prevent that corrosion on the metal. Here is the experimental part. The materials, we use some steel specimens, 836 steel type, and we synthesize the methionine functionalized pool aspartic acid. it's a very straightforward synthesizing process. It starts with the aspartic acid, which is one of the amino acid, and it also polyaspartic acid. We selected polyaspartic acid because it has a long chain structures and it has a multiple absorption sites to provide the better inhibition for the corrosion. Moreover, they have some properties common to the biopolymers derived from the microorganism, plants, or something different things. It's totally biodegradable and non-toxic materials. And we select the methionine, which is the again the amino acid that contain the sulfur atom in its structure, because based on my previous research, previous analysis, and according to literature, if there's some heteroatoms like nitrogen, oxygen, sulfur enhances these atoms provide a more absorption site and provide good corrosion inhibition for the inhibitors. For the experimentals, I will present the three of them. First one is the weight loss measurements. It's done to measure the weight changes over the immersion period to evaluate the corrosion rates. And we use the again A36 steel specimens, and we use as a corrosive environment 0.5 molar hydrochloric acid. And there are some different solutions I prepared. First one is the control only hydrochloric acid without inhibitor, and the other ones is again the hydrochloric acid, but this time adding some inhibitor, methionine function as polyaspartic acid at different concentration. And we performed this test at different for different duration, 1, 3, and 7 days. Second one is the electrochemical impedance spectroscopy. It's the measurement the charge transfer resistance to evaluate the corrosion rates. And last one is the scanning electron microscopy. It's kind of the analyzing surface morphology after the exposure to corrosion conditions. Here's the results for the weight loss. This is for the weight loss analysis for methionine functionalized polyaspartic acid for 3 different duration time. And all these bars shows the different concentration. And it's, as you can see, it's obtained for all duration times. We get the increasing trend as the concentration increases. And the highest concentration was the 500 milligram per liter. And this is the results for that highest concentration for both polyaspartic acid and the methionine functionalized polyaspartic acid, to just show if the functionalization shows better results or not. And the blue one for the polyaspartic acid, and for all the duration times, methionine functionalized one shows the superior, more inhibition efficiency in terms of the decreasing the corrosion rate. So it shows having the good heteroatoms in the structure provides some adsorption sites and the better corrosion inhibition. This is the electrochemical corrosion mechanism in acidic media for the metals. Corrosion is fundamentally an electrochemical reactions involving these electron transfer from iron to the oxidizing agents. And these agents in the acidic media is the hydrogen ions. So this corrosion rates depends on how these electrons are transferred at the metal to that interface. So if we can measure that charge transfer, or if we can say that it can be blocked or significantly reduce that charge transfer, we can say that there is a decrease in the corrosion rate. For this reason, we did the electrochemical impedance spectroscopy test. This is the Nyquist plot of the steel specimen in the hydrochloric acid again, but with different inhibitors, concentration of the inhibitors. And the radius of these Nyquist plot shows the charge transfer resistance. And the higher charge transfer resistance indicates the less electron exchange. I mean, there's more resistance to that electron transfers. So we have the black one is the for the control. There's no inhibitor. So we have the very small diameter. So it shows the lower charge transfer resistance. But when we look at the highest concentration of this inhibitor, we get the higher diameter, which shows the very resistance to more resistance to that charge transfer. And this is the results for the surface morphology. We have three different cases. First one is the polished specimen. We have some scratch on the surface, but it's coming from the polish during the polishing process. The second one is the specimen, steel specimen, immersed in the only 0.5 molar hydrochloric acid. So there are a lot of corrosion products on the surface. And the third one is the again the hydrochloric acid, but this time adding some inhibitors in that solution. Again, we have some corrosive species, some products, but this time we get some more smooth surface when comparing to only the hydrochloric acid case, and which shows the again it's adsorbed on the surface and shows the decreased corrosion rate, gives the higher inhibition efficiency for that metals. This is the representation of the mechanism of this inhibitor, how this inhibitor protect the metals. As I said before, this is the inhibitor mechanism is basically creating the film on the surface to protect the surface, and this protection, this adsorption is coming from the chemical adsorption and the physical adsorption from its structural atoms, etc. And here is the conclusion. We can say that this inhibitor functionized inhibitor efficient and environmental friendly for the A36 steel type of inhibit corrosion mechanism, and it supports the sustainable and environmentally responsible practices. It's, I think, potential to replace that toxic inhibitors that is mostly used in the industry. Thank you for your attention. If you have any question, I'm glad to answer that.
Thank you very much. Questions or comments? So one question from my side. So multiple times you said that existing inhibitors are bad, toxic, or non-sustainable. Can you be a bit more specific? What is their CO2 footprint versus yours, or what exactly is toxic about them?
For example, they contain mostly zinc or other type of the metals, and it's harmful for the soils. I'm talking about the soils because I'm working on the oil and gas industry pipeline, so it's embedded to the soils, so it's harmful for that environment. Not exactly for the CO2 print or something. I don't have that data for now, but I can say specifically for the zinc or some chromat things.
So I would, just my 2 cents, I would suggest that you check this a little bit, because most corrosion inhibitors that I know are pretty simple things.
Okay.
They're widely available chemicals. Like, for example, do you know what one of the most common corrosion inhibitors, at least for concrete, right? Maybe you're talking about a different field, but at least for concrete, do you know what one of the most common corrosion inhibitors is?
For the corrosion, I don't know, but I know for that oil and gas industry, chromat based and the amine based is mostly used.
Okay. So then maybe elaborate on that just a little bit, because a lot of people, if they want to talk about something, they just say that the other thing is toxic or non-sustainable, etc. But when you have a little bit more data on that, I think you can
Uh,
stronger.
okay. Thank you so much. Yeah.
Thank
so
you.
much.
Any other questions or comments, please? Okay, thank you. Zhiliang,
Yes.
all yours.
Do you have my screens now? Okay, good morning, everyone. My name is Zhiliang. I'm super glad to present my research work to you today. And I'm working in the group of Dr. Xianming Shi. And my work is also about metal corrosion resistance. I'm focusing on the rebar corrosion, rebar protection. I'm using sacrificial anodes to do that. And today, my presentation topic is about manufacturing durable sacrificial anodes by using biochars with excellent electrolyte buffering capabilities. I would like to go through the whole story with you. Sacrificial anodes were used in salt contaminated concrete to protect the steel rebars from corrosion. The sacrificial anodes, basically made of zinc, are able to produce and deliver current flows to the rivers, so the rivers are protected by the anodes. However, these sacrificial anodes usually have poor durability with reduced protective current over time because a lot of anodes products are produced at the surfaces of sacrificial anodes. You can see this phenomenon in these pictures where the produced zinc oxide or zinc hydroxide, they can cover the anode surfaces as a solid state barriers. So these barriers can stop the anode reactions. This is why the sacrificial anodes fail inside the concrete. To solve this problem, some past studies proposed two methods. One is to increase the pH value of the electrolytes near the sacrificial anodes, which can increase the solubility of anodic products. So you can see these reaction equations. The zinc oxide reacts with hydroxide, it becomes ions. It's a complex is ions. So the formed solid state barriers can be dissolved as ions. The other method is to increase the porosity of semi-based matrix, because higher porosity can not only reduce the ionic resistivity, but also provide enough space for the barrier storage. And our past studies have shown the high effectiveness of these two methods in anode modifications. Our experiments data shown here indicates the anode's performance can be significantly enhanced with high pH value close to pH 5. It's close to pH 15. It's very high, very high pH value, and the anode's performance can also be enhanced by the higher porosity and even more than 20%. However, these two proposed methods are not perfect. It were found that with the increased pH value and the increased porosity, the protection levels of sacrificial anodes are extremely high at the initial time, but their long-term protection levels are reduced and not sufficient. And our experimental data confirmed the initially high current flow and the reduced long-time performance. So we need to do something. We need to further modify the sacrificial anodes. In this part of my research, we proposed a new methods that is to incorporate some biochars into this system. The biochar is a porous aggregate. It can not only increase the porosity of semi-based matrix, but also enables internal curing effect. In my case, the internal curing effect of a biochar refers to the electrolyte buffering effect. That is, the biochar can store some electrolytes at the initial time and gradually release them to the external environment over a long time. So our hypothesis is that the initial performance of sacrificial anodes should be limited and its durability should be enhanced with biochars. In this research, we considered two kinds of biochars. It is called the ISD and the OR biochars. They are very highly porous, and the SEM pictures can show that. And their water absorption rates are high, and one is over 110%, the other is over 233%. Their sizes are ranging from 100 micrometers to even millimeters. And second, sorry, my laptop is stuck. Okay, second, I'm sorry. At first, we mixed this biochars within the cement-based paste materials, and the foaming agent is also used to increase the porosity of cement-based materials. This page shows the physical properties of the paste samples with biochar and foaming agent. The result shows that with the biochar addition and the foaming agent addition, the compressive mechanical strength is significantly reduced, and the porosity is increased. The gas permeability and the water absorptivity are increased. This is because of the biochar porous. This is because the foaming agent can make a lot of bubbles inside the matrix. All of these results show the cement-based matrix became porous. And second, we selected several mixed designs for preparing sacrificial anodes. As illustrated in these pictures, the sacrificial anode is made of zinc that is embedded into the paste blocks. And the SEM images show the interface between the sacrificial anodes and the outside matrix that is porous. And third, the prepared sacrificial anodes were embedded into the reinforced motors for rebar protection, and the corrosion condition with steel rebars is measured over time. This page gives you all the experimental results. I used 6 parameters to evaluate the effectiveness of sacrificial anodes, and let's get into the point directly. The figure 1 indicates the rebar corrosion condition. The reduced value can indicate the lowered rebar corrosion contaction that is higher protection levels from the sacrificial anodes. We can see that those data with colors means the sacrificial anodes with biochar addition. It has lower values, indicating this biochar embedded sacrificial anodes can produce a higher protection level for rebars. And figure 2 gives you the activity of sacrificial anodes. And we can see that the higher value, we can see that the color boxes have higher values. It means that the biochar addition can significantly increase the electrochemical activity of sacrificial anodes. And this result can demonstrate the overall activity and the overall protection levels of sacrificial anodes because of the biochar addition. And more importantly, we considered the initial performance and the long-term performance of sacrificial anodes in rebar protection. It can be observed that for the sacrificial anodes without biochar addition, they had higher initial property, but decreased the long-term performance. And differently, with the biochar addition, the sacrificial anodes have a limited initial property, but their long-term performance is significantly enhanced. And this research confirmed our hypothesis. This is because the biochar can absorb a lot of electrolytes at the initial time, so it decreases the pH value of outside matrix. And however, over a long time, the absorbed electrolytes can come out to increase the pH value of the external environment. So the anode's activity is enhanced during the long term. This point is also proved through the EIS measurements. which can indicate the surface resistance of the sacrificial anodes. We can see from these results, the surface resistance of anodes without biochar increased over time. This can suggest the gradually formed solid state barriers on the surfaces of sacrificial anodes. However, for the sacrificial anodes with the biochar addition, their surface resistance values increased initially, but significantly decreased during the long term. And this can indicate the electrolyte buffering ability of the biochars. This is because the electrolyte stored in the biochar can come out during the long term and dissolve the solid state barriers on the surfaces of the sacrificial anodes. And furthermore, the SEM and the EDX results show the distribution of anodic barriers. It can be seen that some special biochars have a high zinc. Some special biochars have very high zinc absorptivities, and we guess that this special biochar have graphene oxide-like structures in which some functional groups can grab zinc ions. These special structures are very helpful in dispersing anode barriers. So in the future study, I think we can try to produce some special biochar with graphene oxide-like structures. I think it can further modify the sacrificial anodes. Let's make conclusions finally. The biochar has very high porosity values and excellent electrolyte buffering ability. So it helps to limit the initial performance and contributes to enhancing the long-term durability of sacrificial anodes. And especially gel-like biochars can facilitate the transport and dispersion of some anodic products. That is my presentation, and thank you so much. And looking forward to your questions. Thank you.
Thank you very much. Any questions or comments? So a quick question from my side. Any reason why biochar? I mean, there's a lot of materials around, right? Why did you choose biochar?
Okay. Honestly, when I do this project, I was looking for porous aggregates. It is called lightweight aggregates. And you know, Dr. Xianming Shi is doing a lot of biochar, so I directly use the biochar. And alternatively, I think I can also use some lightweight ceramics, but I didn't try that.
And what kind of biochar was this?
It is called ISD biochar, and another one is Oregon-based biochar. They are made of I think it's the burned weight.
Gotcha.
Yeah.
Any other questions or comments? Okay, I don't see anything. So thank you very much again for doing this. Thank you to everyone and take care.
Thank you.
Yeah. See you. Bye-bye.